Dear student, welcome back for my next lecture, and today I am going to deal with electromagnetic waves in free space. That is, I am going to derive the equation for the electromagnetic waves in the free space, where all of you must be knowing that the velocity of the light in the free space is 3 into 10 power 8 meter per second. So how that velocity of light have been established theoretically, and then again it was established experimentally. So this is what we are going to look into this lecture. At the outset, I wish all of you a happy Ram Navami. I understand this is a very difficult period with which all of us are going. Say this disease is such that spreading. All of us will have to fight it together. And whatever you can do at your end, you should do. Whatever I can do at my end, I am doing. In that connection, I would like to request you again, because since, as I told you, we are passing through a difficult time, so knowledge should not stop. So whatever the video lecture I am posting, I will suggest that all of you should go through it, and even if you are required, you should try to help out to your friends, maybe from your college, the friends maybe from the other college. Even you may forward my video so that community at a large should get benefited. Alright, so let's start with the electromagnetic waves in free space. So let us suppose we are taking a space which is free of the charge. So we have not taken any charge in that medium, and that is the condition for your syllabus. So it's a charge free medium. It does not mean that we have always the charge free medium. We'll have the medium with the charge also, and for that we'll have the different type of the electromagnetic waves. So let us suppose we are taking any medium which is free of the charge, right? But that medium has the dielectric constant, that is, it has got the permittivity, dielectric constant, and permeability, conductivity, everything. So conductivity we have taken as a sigma, permeability we have taken as the mu, and the dielectric constant, which we are also calling the permittivity, we have taken as epsilon. These are the constant that we have taken. So of course, as I have told you that Gauss four equations, which was given by the different scientists, but mathematically it was compiled by Maxwell, and we are going to use all these four equations, which has been finally we compiled by Maxwell, to derive what will be the wave equation of the electromagnetic wave in free, that is the space free from the charge. All right. So let's see what is our first equation. Our first equation is the Gauss Law of Electrostatics, where we say del dot E or del dot D is equal to rho. If I am saying del dot E, then it will become rho upon epsilon naught. All right. So this is your Gauss Law of Electrostatics. This is the differential form that we are aware, and this is your first law. Second law is Gauss Law of Magnetostatics, that is the total magnetic field coming out from the bar magnet or any surface of the magnet is coming out to be zero. So this is Gauss Law for magnetism. This is the Faraday Law of electromagnetic induction, that is the rate of change of the magnetic field is going to induce EMF, and that EMF is represented by the line integral of the electric field, and that line integral of the electric field has been converted in terms of the EMF, that is differential form. So that we are calling as del cross E, because it signifies the curve, and this is called your Faraday Law of electromagnetic induction. And fourth, we have modified Ampere circuital law. So again, here we are saying this is your magnetic field, rotating magnetic field around a current carrying coil, is equal to J. J is your current density that we had taken, that is the total charge enclosed by the wire, and this is the concept of the displacement current, that is the rate of change of electric flux. So this is your rate of change of electric flux, which has been introduced by Maxwell, and therefore it is called the Ampere's Maxwell equations, because the Ampere circuital law was modified by Maxwell, as all of you are aware. So these four equations I am going to use to derive the equation for electromagnetic waves. Now you see, look at the first equation. What we are saying, del dot D is equal to rho, but here what we are saying, where rho is the charge density. What is the rho? Rho is the charge density. But moment we are saying it's a free from the charge, it does mean this value is coming out to be 0. So whether we say del dot D or we say del dot E, that value is finally is going to come to 0, right? So from this we are proceeding. Wherever required, I will put that value to be 0. All right. So let's proceed from one by one. From all the equations we are going to look into again, and then we are going to use that and find out the equation. So let's see further. So from the first law, that is Gauss law of electrostatics, what you say, del dot D is equal to 0. So or what you can say, del dot E is equal to 0, because what we are saying, there is no charge. This is free from charge. So therefore we have written del dot E is equal to 0. It is free from the charge. All right. So this is your, now I am calling this as equation number 1A. New name I have given. So this equation I am calling as 1A. Again from the equation number 2, what you say, del dot B is equal to 0. So B equal to mu into H, right? So again we can say del dot H is equal to 0. So whether we require to apply del dot B or del dot H, accordingly you will see there and we will apply. Then let's come to the third law. So from the third law, so first here I have taken the fourth law, no problem. So this is your Ampere circuital law. So what we are saying, del cross H is equal to J. What is the J? The total current which is circulating the wire, and this is your rate of change of electric field, del D upon del T. All right. So this I am going to write in terms of the charge density. So del cross H is equal to sigma into E. J is equal to sigma into E. What we have taken? J is equal to sigma into E, and this D has been converted in terms of the electric field E. So D is equal to epsilon into E. So this is what we have taken. It has been multiplied by epsilon. So del E upon del T. So this I am calling as equation third A, and all of you must be remember J is equal to sigma into E. We will be using this in the numerical problems also. Now let's one equation is left out. So let's see that equation also. That is your third equation. And that third equation was your Faraday law of electromagnetic induction. So what we are saying, del cross E is equal to minus del B upon del T, rate of change of the magnetic field or magnetic flux. So this B again I am converting in form of the H. So what we can say, B equal to mu into H. So del cross E is equal to mu and del H upon del T. So these are the four equations, 1A, 2A, 3A and 4A, that we are going to use to derive the equations. Now let us see what I am going to do. I am going to take the curl on both sides of the equation 3 and equation 4, and using that curl concept I am going to derive this value. So let us see this. So taking the curl from in the equation number 4. So left hand side you take the curl on this. All right. So what will be this? Del cross E. So what will have? Del cross E. So let's take the curl of this. So what we are saying on this equation, on this side here I am taking the curl. So what we can say, del cross E. I have taken the curl. Then this is equal to how much? What is the value? Mu. This is your mu, right? And then take the curl on the right hand side also. So del upon del T I have taken outside of the bracket, and then I am taking the curl with del and H. So del cross H. So here I have taken on the right hand side. So mu I have taken common, del upon del T I have taken outside. So this becomes rate of change of curl. Here this becomes your rate of change of curl. So what we can say here, this is also your curl. This is your curl, del cross E is equal to minus mu, right? Del upon del T that we are taking from here, del upon del T we are taking over from here, and then I am taking the curl with that. So del cross H. So this is what we have taken. Now this is your vector identity. Del cross E, as you can see, is a vector triple product, right? So it's a vector identity. So let's write down the value of this. So if I'm going to use the vector identity, let us suppose instead of E, I have taken the vector identity as A. So del cross A, then this is written as del dot A minus del square A. So this is the formula that you must remember. Del cross A is equal to del dot A minus del square A. Right? Okay. So I'm going to use this identity here. Here I am going to use this identity. So what I require to do, instead of A, I have to write E. So let's write down. Let's write down. So this is what I have written. Del cross E is equal to what I can write. This is what I have written here. Del dot E minus del square E. So as it is, this two identity has been taken out. Right? So I have transformed this identity into this. That is, A I have replaced with E. So naturally this identity is equal to how much? This is equal to this much. So let's substitute that value. So what we can say, that value is coming. So this value I have brought it here. So what I am saying, minus mu del upon del T del cross H. Right? Okay. Now let's move further with the calculation. So del dot E, this is what I have written. Del dot E is equal to, this is the value. So I have written it again. I have not done anything, just I have written it again. Right? This value I have taken again. Now you see your equation number 1. In the equation number 1, what you are saying, del dot E, since it is free from the charge, so del dot E is equal to 0. So what I have taken, this value I am taking del dot E is equal to 0. Right? So if 0 is going to multiply with this del operator, this value is going to be 0. So I have taken that value 0. So what is left out? Minus del square E. What is left out is minus del square E. This is left out. That value is coming out equal to minus of this. Minus of this value is left out. So what I'm going to do, both side minus and minus I'm going to cancel. So this minus and minus has got cancelled. So finally what I'm getting, del square E is equal to mu del upon del T plus, now let's see further, del cross H. Now you see equation number 3 here, 3a, del cross H, this is your Ampere circuital law. So del cross H is equal to how much? Sigma E. So this is what value that I have substituted here. Del cross H, the value of the del cross H I have substituted from equation number 3a. So this value has come from the equation number 3a. This is the 3a that I have used. So from 3a I have got the value of del cross H and I have substituted this. So finally what is the value I am saying? Del cross E is equal to mu del upon del T sigma E plus epsilon del E upon del T. Alright. So this is your equation for electric field. This is the equation for changing electric field, where del square is equal to how much? Del square is equal to del square upon del square x, del square x plus del square upon del square y, del square upon del square y, del square y, plus similarly del square plus del square z, plus del square, very difficult to write from this, upon del square z. Alright. So because we know del equal to del upon del x plus del upon del y plus del upon del z. So del square will equal to del square upon del square x plus del square upon del square y plus del square upon del square z into E. Right? If I am going to take into the only one direction, let us suppose I want to find this for only x direction, the propagating wave only in x direction. So this value will be 0. So this equation will be coming out as del square upon del square x E. If I am going to take only for the x direction, then this equation I can write del square upon del square x into E is equal to this value. Whatever you have on the right hand side, that value will come. Alright. So this is for your electric components. Now similarly what I had done here, I have taken the curl, you see here, I have taken curl in fourth equation. Similarly what I can do, I can take curl in the third equation also. Here I can take again the curl. So if I am going to take the curl over here, then what we can write, del cross del cross H. As I have written here, del cross E. What I can write here? Del cross H, right? And then similarly we can solve this, and then we will be finding out some equation like this. So what is the equation that I am going to find out? This is the equation that I am going to find out for the del square H. That is, this is for your magnetic field. So mu sigma del H upon del T plus del square H upon del T square. This is the equation that I am going to get for magnetic field, right? Now let us proceed further. So therefore, the electromagnetic waves can be given as, this is for your electric component, del square E is equal to mu sigma del E upon del T plus mu epsilon del square E upon del T square. This is for your electric component, right? And here you have calculated for your magnetic component. So magnetic component is this, del square H is equal to mu sigma del H upon del T plus mu epsilon del square H upon del T square. That is, again I am repeating, del square E is equal to mu sigma del E upon del T plus mu epsilon del square E upon del T square. And del square H is equal to how much? Mu sigma del H upon del T plus mu epsilon del square H upon del T square, where all these symbols have their usual meaning. Alright, so this is the equation for your electromagnetic waves, where both the electric components and magnetic components are always together. That with the graphical representation, maybe I will show you in the next class. Now let's find out what is the equation of velocity of light in the free space. This is what I am going to do this. Now in case of free space, in case if I am taking completely free space, then this value of the sigma will become 0. In the free space you don't have the sigma, so this value of the sigma is 0, and here also this value of the sigma is equal to 0. So moment I am going to put this value of the sigma 0, then this term is going to be 0, fine, and again this term is going to be 0. Why it is going to be 0? Because it is free from any conducting medium. This is for the non-conducting medium. So this is what is the definition of the free space. So in case of the free space, the value of the sigma is equal to 0. So I have just removed that. Then what I am getting, del square is equal to mu epsilon del square E upon del T square. This is one equation, and del square H upon del T square is equal, del square H is equal to mu and that is and epsilon del square H upon del T square. So these are your two equations for the electromagnetic wave if it is completely non-conducting medium. All right. Now let's proceed further. Now the general equation. Now what I'm going to do, I have to find out what is the, how this is going to correlate with the velocity of the light, mu epsilon. So the general equation, if let us suppose if any wave is traveling, let us suppose you have here you have got a string, right, which is supported in a wall. So this is, you have taken a string, this is supported in a wall, and you have disturbed this string like this. You have put your finger on this, you have oscillated. Then what will happen? A wave is getting set up on your string, and wave does move like this. So what is happening in this direction? Positive x direction, wave is moving, and here it will have a particular value of the magnitude. Let us suppose this is your electric field. This is your electric field. Similarly, we will have the magnetic field, right? So here I'm not that maybe I will taking up in detail in the next class. So this will be your another field, and which I am calling this your magnetic field. So here we have the two field. One is your electric field. This field I am calling as the electric field. Electric field and magnetic field are always perpendicular to each other. So this is your electric field, and this is your magnetic field. This is your magnetic field. So let us suppose I am representing this by H. So equation of the electric field is this. In this, whatever you have got this, the equation for the electric field is this, right? And equation for the magnetic field is this. This is your equation for your magnetic field, right? This is how you are getting the electromagnetic waves. So what is the general equation for if any wave is traveling in any one particular direction, then this is being given as del square A upon del x square, where del square A does mean it is only along the one direction, that is x direction, and here this del does mean it is in the 3 dimension, right? So that I have already explained you is given by 1 upon V square del square A upon del T square. This is the equation, general equation. So what we can do, I can equate this equation with any of these two equations, right? Then what I can say, 1 upon here, this is also your coefficient. This is also the coefficient of your vector A, and this is also the coefficient of your vector E or vector H, right? This is the coefficient of vector E or vector H. So naturally 1 upon V square is equal to what we can write, mu epsilon. This is what the value I can write. So this is what I am telling. Here I have written V is equal to 1 upon mu naught epsilon naught, because if it is the permittivity here, then we have to take the absolute medium. So this value will become mu naught, this value will become epsilon naught, this value will also your mu naught, this value will be your epsilon naught, right? So comparing with this, what we are saying, V is equal to 1 upon mu naught upon into epsilon naught. So V is equal to 1 upon mu naught epsilon naught. This is the velocity. If you are going to substitute the value of mu naught and epsilon naught, then you will be getting the velocity of the light, and that velocity of the light will be coming out equal to 3 into 10 power 8 meter per second. Maybe one more slide I will see in the next class on this. So for today, thank you very much. Enjoy your Ram Navami. Thank you very much.